Hello everyone. In this video, I'll explain the mechanism how scan chains are used to detect stuck-at faults in a design. Before we begin, I would like to mention that this explanation assumes you're already familiar with scan chains and their properties. This background knowledge is essential to understand how scan chains enable fault detection in a design. If you're not familiar with these concepts and you would like a quick refresher, please watch my other video. In that video, I explain what scan chains are and how they are useful in chip testing and fault detection. Now let's move on to fault testing scenario. Assume that a die has been manufactured and we want to check whether there are stuck-at faults in the design. To perform this testing, we make use of the scan chains present in the design. Consider a scan chain in the design consisting of three scan flip-flops, or commonly referred as scan cells, SFF1, SFF2, and SFF3, as shown in the diagram. The pin connection for each scan cell, data input D, clock input CLK, scan input SI, scan enable SE, and output Q are also shown in the figure. The block diagram of the scan cell that is commonly used marks T scan cell is also shown here. Each scan cell contains a multiplexer at its input based on the value of the scan enable SE. Either the functional data input D or the scan input SI is selected and stored in the flip-flop. When scan enable is 0, the scan cell operates in functional mode. The D to Q path is active. The value present at D is captured on the active clock edge and appears at output Q. When scan enable is 1, the scan cell operates in scan mode. The value present at scan input SI is captured and propagated to Q on active clock edge. When the scan enable signal of all the scan cells are tied together and driven from a common scan enable port SE, setting SE equal to 1 causes the connected scan cells to behave like a chain of shift registers. This operating condition, where scan enable port SE equals to 1, is commonly referred as shift mode in the scan chain. Now let's assume that in this design there is an AND gate in this combinational logic sitting between scan cell 1 and scan cell 2. We want to test whether node P, which is the output of this AND gate, is stuck at logic 0 or not. To detect the stuck-at fault in the design, the scan chain is operated in a specific sequence. First, it is operated in shift mode, then capture mode, and then back again to shift mode. Let's discuss these steps one by one. In the first step, the scan chain is placed in shift mode to load the desired test pattern into the scan cells. To do this, we apply test pattern at scan input port SI and set scan enable input port SE to 1. Then run the clock for certain clock cycles, depending on the scan chain length. This makes the values at scan input port SI shift through the scan chain and appear at the Q outputs of the scan cells. Over here in this example, in order to test whether node P in the AND cell is stuck at 0, we should drive both the inputs of the AND gate to logic 1, where one input is driven by SFF1Q and the other input is driven directly from primary input B2. To set SFF1Q equals to 1, we apply a certain test pattern, for example 101, at the scan input port and run the scan chain in shift mode for 3 clock cycles. This results in SFF1Q equals to 1, SFF2Q equals to 0, and SFF3Q equals to 1. We also drive the other input of the AND gate to logic 1 by setting the primary input port B2 to 1. At this point, the complete test pattern is successfully loaded into the design. After shifting the test pattern through the scan chain, we switch the scan chain to capture mode by setting scan enable port SE equals to 0. We set SE equals to 0 only for one clock cycle. In this capture mode, all the scan cells operate in normal functional mode, where the D to Q path is active. The combinational logic evaluates the applied test inputs, and the resulting values at the D input of the scan cells are captured on the active clock edge. In this example, if we applied input combination 1 1 to this AND gate, a fault-free circuit would produce an output of 1. However, a circuit with stuck at 0 fault at node P would produce an output of 0. This faulty value appears at the D input of the scan cell SFF2 connected to node P and is captured into SFF2Q during the capture clock cycle. After capturing the response, we return the scan chain to shift mode by setting SE equals to 1 again to observe the circuit response. The captured values are then shifted out through the scan chain and appear at the scan output port. In any circuit, the captured response reaches to the scan output port in at most n clock cycles, where n is the length of the scan chain. By observing the value at SO port and comparing it with the expected response, we can determine whether the circuit is faulty or not. In this example, receiving a 0 instead of an expected 1 indicates the presence of a stuck at fault at tested node P in the combinational logic block. By repeatedly applying the sequence shift, capture, and shift on the scan chain, we can test the circuit using multiple test patterns. While shifting out the captured response, we can simultaneously shift in the next test pattern at the SI port. For example, if the first test pattern was 101, the next pattern can be 111. This creates a continuous sequence of shift, capture, executed for as many test patterns as required. If the captured response does not match the expected result, the chip is identified as faulty. This is all for this video. I hope this explanation is helpful.